Yes, good evening again. See, today we are going to see the solutions for the multiple choice questions in your book. That is in the unit number 3, magnetism and magnetic effects of electric current. Okay, and it is for your class 12th. Okay, now we'll see the solutions for these particular problems 11 to 15. I have already posted the solution for the question from 7 to 10. Okay, so this is the question now. The BH curve for a ferromagnetic material is shown in the figure. The material is placed inside a long solenoid which contains 1000 turns per cm. The current that should be passed in the solenoid to demagnetize the ferromagnet completely is. See, what they're asking is they want to demagnetize a ferromagnet which is already a magnet. Okay, the same solenoid only they would have magnetized this particular material. Okay, so they are given this uh, hysteresis curve. This curve is called as a hysteresis curve. Okay, so this hysteresis curve will give you the behavior of the magnetism or magnetic properties induced in the material, how it is been induced and how it is magnetized and how it can be demagnetized. So that particular history it will give. For example, see this is the for example this is a ferromagnetic material you take. Okay, this is a ferromagnetic material. How will you make it a magnet? This is a um, ferromagnetic material. Okay, so which can be made into a bar magnet, into a magnet. How will you make it? Okay, so this one I'll be uh, over which I'll be winding with a solenoid. So a coil like this. Okay, so I'll be passing current through this. Okay, and this when the current is passed through that at the center of the solenoid, okay, you will get the magnetic field that is called H. Okay, so this H only is going to make this particular magnet uh, into a magnet. Okay, it will convert this particular bar ferromagnetic material magnet. Okay, that is bar material into a magnet like this, which will have this B. So this graph here it is drawn between H. Okay, this is between H and B. So how H is given and how this particular material is becoming magnet. So H is depending on this current. Okay, so when I pass current in this direction, this H will be in this direction, so it will be increasing along the x-axis. So when I reverse the current, okay, instead of passing it when I reverse the current in the opposite direction like this, okay, when I reverse it, what happens, this H will be in this opposite direction, so this will be minus H. Okay, so when I pass current in this direction, it will get magnetized, and when I want to remove it, demagnetized material, I have to pass the current in the reverse direction, so that I get this minus H, because it is an ampere. Okay, ampere per meter. Okay, how much ampere I'm giving per meter of this coil. Okay, so that will become the H. So this H value, okay, only will depend, which makes this particular material into a magnet. Okay, and this H value will become okay, even though if I increase the I value, the H value uh, will not increase. Okay, even if this is increasing, this magnetic induction, okay, magnetic induction or magnetic flux induced inside this bar magnet will not rise certain level, will not rise beyond certain level. So this point, okay, say for example here it is 200. If you understand, if you observe this graph, it is 200. So it is 200 ampere per meter. If I further increase this H, okay, this B is not going to increase. This magnetic induction which is being induced inside this bar magnet is not going to increase. So that this point is called saturation point. Okay. So beyond this, even though if you increase this H, the B will not increase. So it will be steady only. It will go like this. Okay. So if I want to demagnetize it, so at this particular point, this particular material has become completely magnet. Now it's become a bar magnet. Now if I want to demagnetize it, then if I reverse this current, this solenoid, what happens? This H will come in the opposite direction, so that this demagnetization will not reach the origin, because initially while I was magnetizing, this curve was like this. So it started from 0 and reached this point, that is a saturation point. When I reverse it, it will not follow the same path, but it will follow this path. Okay, at this point, no, at this point, even though the H is 0, this magnetic induction or the magnetic intensity, this magnet is not 0, it is 2. So to remove that uh, 2 Tesla, okay, so this is called the retention. So this amount of magnetism or magnetic property is there, okay, that is called retention or retensivity. Okay, so I want to remove that. So I will be introducing the current in the opposite direction. Okay, and it will get magnetized at this particular point. So as per this graph, it is 150 amperes. So at this 150 amperes in the negative direction, this particular material has completely become demagnetized. That's what you have to understand from this graph. So this the graph is given to take only this data. This data of 150 amperes I should observe. So A ampere equal to minus, that is 150 amperes. Okay, A. So after taking this data, see what the question they have asked. The current that should be passed in the solenoid to demagnetize a ferromagnet completely. Okay, so this is the amount of current it takes per meter. Okay, so here they are given the uh, condition of this solenoid. Okay, which contains 1000 turns per centimeter. So it is this solenoid is having 1000 turns. Okay, 1000 turns per centimeter. Okay, so this implies how many turns for 1 meter? For 1 meter, it will be, how many turns would be there? For 1 centimeter, there are 1000 turns. So if I consider this solenoid for 1 meter, so this 1 meter, it will have 1000 into 10 power 3. That is into centimeter. Yes, some centimeter to this meter. So it will be 2, 10 power 2. So it will be having 10 power 5. Okay, it will have 10 power 5 turns per meter. So this is the condition of solenoid now. So in this solenoid, if 10 power 5 turns are there, okay, this 10 power 5 turns takes this 150 amperes. Okay, 150 amperes. So for one turn, that is how much current should be passed in this solenoid to demagnetize a ferromagnetic completely, is how much for one turn. So that is the current here. So what is the current needed will be, so this is the 150 which has been obtained from the graph, and divided by this 105, then there is 10 power 5. Okay, so this will give you the value of current should be passed through this coil. Okay, if I pass this much of current through this in this okay, that too in the opposite direction, so it will get demagnetized at this particular value, minus 150. Okay, so if I simplify this 150, I can write it as 1.5. Okay, 1.5 into 10 power 2 divided by 10 power 5. So this will, so 10 power 2 minus 10 power 5 become 10 power minus 3. So it will be 1.5 into 10 power minus 3 amperes. So this is actually 1.5 milliamperes. Okay, 1.5 milliamperes. So if I see the options, the C option is going to be the right answer. Depends on what you. So here what you have to understand is this graph is given to take this value. Okay, there is 150 amperes is for 1 meter of coil. Okay, so that's what this is, a 150 is for 1 meter. So 10 power 5 is for one coil. Okay, this is the amount of current should be passed through one coil. So it is having 10 power 5 coils. Okay, 10 power 5 coils turns are there. Okay, why? Because there are 1000 turns per centimeter. So 1 meter will be 10 power 5. You understand? So the 150 by 10 power 5 will give you the amount of current needed to be passed in the one coil. So this will be the answer. So 1.5 into 10 power 1.5 into 10 power minus 3 amperes, or 1.5 is milliamperes. Okay, we go to the next question. Yes. Now the 12th question. Two bar magnets have magnetic moments 1.2 ampere meter square and 1 ampere meter square respectively. They are kept on a horizontal table parallel to each other with their north poles pointing towards south. Okay, they have a common magnetic equator and are separated by a distance of 20 centimeter. The value of the resultant horizontal magnetic induction at the point O of the line joining their centers is, the horizontal component of earth magnetic induction is 3.6 into 10 power minus 5 Weber per meter square. Okay, so here they are given this two bar magnets, okay, two short bar magnets which is having this magnetic moment of 1.2 ampere meter square, and the other one is having 1 ampere meter square, and they are kept on a table horizontally, and with their north poles are pointing toward the south. So south poles, these two north poles are facing the south pole. Okay, geographic south, and they have the common magnetic equator and separated by the 20 centimeter. Okay, so the distance between these two magnets is 20. Okay, the value of the resultant horizontal. So they are asking to find out. They are asking you to find out the magnetic induction at the midpoint of these two bar magnets. Okay, so assume this is the one bar magnet like this. Okay, this one, and another bar magnet like this, and this one is having magnetic magnetic moment of 1.2, okay, ampere meter square, and this one is having pm is 1 ampere meter square. Okay, so these are two bar magnets, and the distance between these two bar magnet is 20 centimeter. Okay, so there is a equator line like this. So there is the equator line, the center line. Okay, and this is the center point of two magnets. Center point of two magnets. So line joining these two centers. Okay, this particular point is O. So they are asking the value. What is the value of magnetic induction at this particular point O? So that's a question. So we have to find out the magnetic induction because of these two magnet, and also the horizontal component is also acting in this direction because these two magnets are facing south. So this is the south side. So this is the geographic south. Okay, so this is a geographic south, or the earth magnetic earth south pole. Okay, earth south pole is this side. So these two north poles of this magnet, that's what is given the problem. So these two north poles is facing the south pole of the earth. So this is going to be the south now. Okay, and you know this, the horizontal component of the earth will be towards the south. So this value is also given. What is that? 3.6. So 3.6 into 10 power 5. So this is the BH value is given. Okay, so 3.6 into 10 power minus 5 is given. So it is acting in this direction. So this is BH. Okay, and if I take this is the B1. So B1 is the magnetic induction due to this magnet 1, and this is the B2. Okay, by the second magnet. So how the magnetic field lines will flow actually? So the field lines will be like this. Okay, from the north pole to south pole. So from north pole to south pole like this. Okay, north pole to south pole in this direction, and when I take it above this magnet, it will be this side. So I'm taking one line. So one more line from the B2, that is second magnet. Okay, so if you take it like this, so here this take this color. So this magnetic field line will be north to south like this. So these, you can see these two magnetic fields are the same direction, and BH. So B1, B2 and BH are the same direction. So it's towards this north. So towards the north, geographic north. You understand? So I have to add to find out this value, okay, of resultant magnetic field at the particular point O, that is B naught. Okay, at this particular point O, I have to add all this vector addition of all these three magnets. Okay, so that will be equal to BH plus B1 plus B2. Okay, so now you should know this, the value of magnetic field, okay, the magnetic induction available at a particular point P. Okay, this is a point P, and this magnet is having a magnetic dipole moment, okay, magnetic moment of PM, that is PM value is 1.2. Okay, and from this center, if I calculate this distance is R, then if I find out the B value here, as per this formula, you know, okay, that is K into Pm by R cube. Okay, this is a formula to find out the magnetic induction. Okay, magnetic induction at a particular point, a particular distance R from the center of this magnet, this bar magnet. Okay, you know this R is given. So, see what is in our case, what is the R value? In our case, the R value is 10. So this is 10 centimeter. Okay, R value is 10 centimeter. So if I find out the magnetic induction at this particular point O, so there are two power magnets. So both are at the same distance, 10 only. Okay, so this 10 centimeter, no, this 10 centimeter is nothing but my 1 into 10 power minus 2 meter. Okay, so this one is R, this is R value. So if I find out the R cube value, this R cube I can write it as uh, okay, 1 into this 10 into 10 power 10 into 10 power minus 2 meters, because this is a 10 centimeter, no, so 10 into 10 power minus 2, so this one I can write it as 1 into 10 power minus 1, okay, R whole cube. Okay, so 1 into 10 power minus 1, so this will become 10 power minus 3. So this is the R cube value. So now if I substitute this okay, in this formula, so BH is directly given, I need not worry. So B1, how can I write this? B1 is K. What is the value of K? It will be 10 power minus 7. Okay, that's a dielectric constant. K value, you know, it is 10 power minus 7. Then PM is the for the first magnet B1 will be equal to 1.2. Okay, so divided by R cube. R cube, what is the value of R cube? R cube is 10 power minus 3. I think you understand this one. Okay, plus B2. What is the B2? B2 again K into 10 power minus 7 into 1. Okay, there is a magnetic moment of the second magnet. Okay, B2. So 1 divided by is in R cube. R cube will be 10 power minus 3. You understand? So this BH is given already. So BH is given in the problem itself, so that I can substitute it directly here. Okay. So this one B naught will be equal to BH. BH is given in the problem itself. What is that? 3.6 into 10 power 5. 10 power minus 5 I can write. Okay. So this one I can write as 0.36. 0.36 into 10 power minus 4. Okay. Plus. So this one 10 power minus 7, this 10 power minus 3 will become what? 10 power minus 4. So this will become 1.2 into 10 power minus 4 plus again this 10 power minus 7, this 10 power minus 3 will become 10 power minus 4. So this will become 1 into 10 power minus 4. For this only, to make this power same, I am just writing this 3.6 into 10 power minus 5 as 3.36 into 10 power minus 4. So now I can add all these things. Okay, 0.36, 1.2 and 1 easily. So 1.2 plus 1 is 2.2. So 2.2 plus 0.36 will be 2.56. So 2.56 into 10 power minus 4. 10 power minus 4 Weber per meter square. So this is going to be the final answer. That is the magnetic induction available at this particular point O. So this point, the magnetic induction available will be 2.56. So if I find out this options in this option, so the C is going to be your answer. So understand, the C is going to be your answer for this particular question. So this only one formula you have to remember here. What is that formula? Is K into Pm by R cube. So that is in the equatorial line. In this equatorial line, at the particular point P with the distance of R, what is the magnetic induction or magnetic field available at this particular point P is given by the formula K into Pm by R cube. This formula only if you understand, if you remember, then I can easily solve this particular problem very easily. Okay, so I have to solve it within a very short time. Okay, go to this problem. Yes, this is also another very easy problem only. So here the vertical component, okay, the vertical component of earth magnetic field at a place is equal to a horizontal component. So what is the value of the angle of dip at this place? So here earth magnetic field at the is equal to the horizontal component. Vertical component also is equal to the vertical component. So BV is equal to BH. Okay, so BV and BH are equal here. So they are asking what is the angle of dip at this particular place, So here this is a BH horizontal component and this is the vertical component BV. Both are equal. Okay, so both are equal means the resultant will be like this. Okay, this is a resultant. What is the value of angle of dip? The resultant is nothing but your angle of dip. So at the angle of theta. Okay, this is the angle of dip. Okay, so angle of dip here, this theta, how can I find out this? Because by tan theta, you know this formula. What is the tan theta? Tan theta will be equal to BV by BH. That's equal to 1. Okay, BV by BH is equal to 1. So because both are equal, the problems they are given, so it is both are equal. So tan theta equal to 1. So tan theta equal to 1 means the theta will be equal to 45. So this is a direct line. Just by seeing this question, I can answer it. So it will be theta equal to 45. You understand? This is how you have to answer the 13th question. Okay. Then, so next one is your this 14th question. Okay, the 14th uh, question. So it is like this. So the flat dielectric disc of radius r carries an excess charge on its surface. The surface charge density is sigma. The disk rotates about an axis perpendicular to its plane, passing through the center with angular velocity omega. Find the magnitude of the torque on the disk if it is placed in a uniform magnetic field whose strength is B, which is directed perpendicular to the axis of rotation. Okay, so here what they are saying, see, there is one flat dielectric disk. Okay, that's a disk like this, and its radius is given r. Okay, r is given, and it is carrying an excess charge on its surface. On the surface it is having some charge density sigma. Okay, the disk rotates about an axis perpendicular to its plane. So about this axis, okay, if I take this as O, it is rotating about this axis, okay, with omega, maybe clockwise or anti-clockwise, like this it is rotating, okay, through the angular velocity omega. Find the magnitude of the torque on the disk if it is placed in a uniform magnetic field whose strength is B, which is directed perpendicular to the axis of rotation. So this is the axis of rotation, and the magnetic field is there. Okay, so this magnetic field is here in this disk, okay, which is perpendicular to the axis of rotation, that is B. Okay, and they are asking what is the torque here. What is the torque on the disk if it is placed in a uniform? So this magnetic field is like this, okay, perpendicular to the axis of rotation, and they are asking to find out the torque. So you know what is the torque value, that is will be IAB. Okay, so I is the current passing through this coil. So this is the passing through this disk. That is how much current is there. Okay. So here they are given only the charge. Okay. So surface density, charge density they are given. It is sigma. Okay. Then I can find out the area of this. So area of the disk will be what, pi r square. Okay. Pi r square, that is A value, and I is this one, sigma. Sigma is a see, I can find out I by sigma, this because the sigma is the charge density. Okay, and when I know the charge density by time, the charge density by time will give you I, because you know I is equal to Q by T. So what is the amount of charge available in this disk? This is actually a disk. Okay, it's a complete disk. So what is the charge available on this disk is the charge density they are given. So sigma for per unit area. Charge density is given for surface charge density. Okay, it is available on this area. You understand? So for if it is available like this, then for the whole area, how much it will be? It will be pi r square. So sigma into pi r square divided by time. Okay, this time I can write it as, okay, you know omega. Omega equal to 2 pi by t. Okay, so from this I can say this t, from this I can say this t value will be equal to 2 pi by omega. Okay, so you know what is omega? Omega is the angular velocity. Okay, angular velocity. So for one's complete cycle 2 pi, how much time it takes? So t. So t will be equal to 2 pi by omega. So this, instead of this t, I can substitute this value. Okay, so this will give you the current value now. So 2 pi by omega. Okay, so this one is charge now. So sigma pi r square is the charge available on the disk, total charge, and by time. So this time is 2 pi by omega. So when I get this ratio, I will be getting the current value. So that value I will be substituting here. So okay, so this is a current which is been available in this disk. Okay, so that will be sigma pi r square by 2 pi by omega. Okay, pi r square by 2 pi by omega into area of the disk will be pi r square. Okay, so here in this area I am taking it as half. Why? Because to find out the torque, okay, the torque which is the one which makes this rotate, makes this disc to rotate. So I am assuming this particular area, okay, is assumed to be at the center of this arc, that is half of this arc. Okay, half of this arc, this I am assuming this whole area is going to be assumed to be concentrated. So this value I'm writing it as that area by 2, left channel of view. So when I simplify this one, okay, that is into this b value. Okay, so this b value is there. Okay, this b is there. So this as per the formula b. Okay, so here uh, if I calculate, if I simplify this, okay, if I simplify this value, what you will get? See, listen here. This pi, yes, this pi and this pi will get cancelled out. Okay, then this r and r square plus r square will become r power 4, and this will become uh, okay, this 2 into 2 will become 1 by 4. Okay, this 2 and this 2 will become 1 by 4, and this is r power 4. Then sigma also you will have, the sigma will have, and this omega will go to the numerator. So 1 by 4 sigma, okay, omega r power 4. This pi only get cancelled. You have one more pi here. So this pi and b, okay, and b. So if I write this in format, the okay, in this option format, if I write it up, so this one I can write it as sigma omega pi b r power 4. Okay, sigma omega pi b r power 4. Okay, so this one I can find out this option as D. So D is the right answer. Okay, so here what they are asking is, this is a disk. This disk is having some charge density. From the charge density I can find out the current. Okay, when I charge, if I know the charge density, and if I divide this charge density by time, I'll get the current. Okay, the torque formula is this one, IAB. So I can find out the current on area. I am taking, so because it is a disk, it is having the current, okay, that is charge all over the surface. I'm taking the half of this area. Okay, so that I'm assuming this particular half of this area, which is gives you the maximum value or maximum force in this particular direction, so that it makes the disk to rotate. Okay, and B is the magnetic field available. Okay, which is magnetic where this disk is being kept. Okay, this is the magnetic field. So when I keep it, this inside this magnetic field, this disk will rotate in this direction. Okay, with the omega. So this direction of rotation, maybe clockwise or anti-clockwise. You understand? So this is going to be the answer. So this option will be 1 by 4 sigma omega pi b r power 4. Okay, we go to the next problem. Okay, so here the 15th problem, the last problem, this one. Okay, the potential energy of magnetic dipole whose dipole moment is Pm equal to minus 0.5 I plus 0.4 J ampere meter square, kept in a uniform magnetic field B equal to 0.2 I Tesla. Okay, so potential energy of the magnetic dipole. What is the formula? You know. Okay, so potential energy, how will you find out? U. Okay, potential energy U will be equal to M dot B. Okay, that is a dot product of moment. Okay, so here I can take this one as Pm. Okay, Pm into B. That is a magnetic moment, magnetic dipole moment into the magnetic field, dot product. So this one is Pm into B cos theta, you know. This part, this actually this potential energy means, so it will be in the minus. Okay, so minus Pm dot B. Okay, this is a formula. This is a formula to find out the magnet. So when it is kept, say this bar magnet is kept inside a magnetic field. Inside a magnetic field, this bar magnet will try to rotate in this direction. Okay, based on these poles. So because of this rotation, okay, it will have initially it will have this potential energy. So that value of potential energy is given by this formula, minus Pm into B into cos theta, or minus Pm dot B. Okay, so here the Pm is given in the problem itself. So minus 0.5 I plus 0.4 J. Okay, so it should be dot producted. Okay, dot product with the b. What is b here? Minus 0.2 I. So if I take the dot product between, see, dot product between 0.5 I and 0.2 j, so angle between this I and I is 0. So if I substitute here this theta equal to 0, then I'll get 1. So pm into b I'll get. So okay, so minus into minus, it is okay, it is plus. So 0.5 into 0.2, it will be 1. Okay, so I will get it as 0.1, okay, plus 0.1 joules. This is going to the potential energy value. So here, uh, this j dot I will be 0, because j dot I, if I take the dot product, the dot product between j and the angle between j and I is 90. Okay, so cos 90 is 0. Okay, so here if I take this cos theta is, in the previous case, I dot I, the theta is 0. Theta is 0 means theta is 0, so cos 0 will be 1. And j dot I, the theta is 90, so cos 90 will be 0. You can understand? So I'll be getting this 0.5 into 0.2 is 0.1. So 0.1 joules is the final answer. So here the option will be 0.1 joules. C is the answer. So the first result they are given is minus 0.1. So if you are not putting this minus to find out the potential energy, so you'll be landing with this answer minus 0.1, so which is wrong. So the answer is 0.1 joules. C option. Okay, thank you. We'll see in the next video the solution for the fourth unit. Thank you very much.